Namaste. In this course, we'll talk about multimodality. So if you could recall, when ChatGPT was released, it could only process text in, text out. But nowadays, most models are multimodal. What do we mean by multimodal? They could actually process multiple modalities. They could process text, they could process voice, they could process images as well as the videos. So how these models became multimodal? So we'll talk about it. The prerequisite for this course is vector embeddings. We discussed in detail what vector embeddings are and why they are used. So I encourage you to watch that video. In short, what vector embeddings are, we assign a space to a word or a sentence in multi-dimensional space, basically 1000-dimensional space. So we assign a coordinate to a word or a sentence. And why do we do that? Once we do that, we calculate the distance between the two words or two sentences. And if distance is less, we say that these two words or sentences are similar in meaning. And if distance is more, we say they are not similar. So that's the concept. So before we proceed, can you answer this question? Should same sentences in different languages have same vector embeddings? I suggest you pause the video for 2-3 seconds and try to answer this question. So the answer should be that they should have, right? Because by vector embeddings, we are actually identifying the semantics. So if two sentences which are in different language, they should have almost the same vector embeddings. For example, if in English the sentence is how are you, and in Hindi the sentence is aap kaise ho, now these two sentences are similar in nature, they have similar meanings, so they should have almost similar embeddings. So if you see, if a sentence is in English, vacation spots in California, and the same sentence in Chinese, we have almost the same embeddings. So if you see, with this technique, embeddings for every language exist in the same vector space and maintain the property that words with similar meanings regardless of language are close together in vector space. So this makes sense. Once we have understood the concept of vector embeddings, now we can relate with this concept. So if you see, if there are words in English and Turkish, you can see soccer, football, they goal, these all have similar embeddings. With this, we have the use case of language translation as well as multilingual search. So we can ask question in English and we can get results in another language as well. So for example, when we ask vacation spots in California in English, we could actually get the information in English and French. So if you specify the language English, we can get the answer in English, and if we specify the language French, we can get the information in French as well. Similarly, we can ask question in any other language and we can get the result in English. So by now you understood that based on these vector embeddings, we can actually do language translation, and because we are capturing vector embeddings of different words or sentences in different languages. Okay. Now, what do we mean by multimodality? In multimodality, same vector embeddings for different modalities. So what do we mean by that? So for example, if we have a text, lion is the king of the jungle, and then we have an image that represents the text, and then we have voice which says the same thing, and then when we have a video which also represents the same text, then all these entities should have same embeddings. This multimodality gave birth to multimodal LLMs, or they are also known as large multimodal models. So what they can do, they can take multiple forms of inputs. They can take text, image, video, or voice as an input, and they can provide output in these modalities as well. So basically they can take multiple forms of inputs and provide multiple forms of output. Earlier we had unimodal models which could only take text as an input and provide answer in text, but now they can take multimodal inputs. For example, describe this picture. So image as well as text, and it can provide results in text. Then draw a picture of cat, text as an input but the answer is in image. Then write a song about a cat, text is in input but the output is in voice. So with this we got multimodal outputs as well. Now we need to talk about multimodal embeddings. How do we create it? So two sentences in different languages will have same vector embeddings, and that's how we understand that these two sentences are similar in meaning. Now we'll apply the same concept for multimodalities. So even if the modalities are different, it could be text, voice, image, or video, but if they are showing or depicting the same thing, their embeddings should be the same. And this is what we want to achieve. So what we'll do, we'll first embed all the modalities in the same 1000 dimensional space. And it could be a text which says lion is the king of the jungle. At the same time, it could be an image of a lion sitting on a rock in a jungle. Now these two are different modalities, but their vector embeddings should be almost the same. So this is what we want to achieve. So how do we do that? We first start with specialist model. So we have text. So the lion is the king of the savannas, or lion is the king of the jungle. We'll encode using text encoder. So, and using image encoder, we'll encode an image. Using audio encoder, we encode a voice, and using video encoder, we encode video. So you can see now when we use specialist model, we get very different embeddings. Now by using a specialist model, we'll bring them closer to each other. And how do we do that? We use a concept called contrastive representational learning. Through contrastive representational learning, we basically unify multimodal embeddings. So what is the process? The process is we first train any embedding model, which basically first start with the unimodality. Then we unify multiple models, create a single vector space. We then fine tune the model by providing contrastive examples. So let's understand how we do this thing. So in contrastive learning, what we do, we have an anchor. So if we are doing contrastive learning for text, we have an anchor that says he could smell the roses. For that anchor, we have a positive example that says a field of fragrant flowers. And then we have a negative example, the lion rode majestically. So the idea here is, for every anchor we provide a positive example. What we mean by positive example is the sentence which is similar in meaning to the anchor, and then a very different sentence acts like a negative example. Now when we embed, you can see that negative is closer to anchor and positive is farther to anchor. Now through contrastive representational learning, we basically, the model understands that positive should go nearer to the anchor and negative example should go farther to the anchor. And this is how we learn. The same concept is applicable to other modalities. So if you see, we have an image of a dog which is our anchor. Now image of another dog is our positive example, and any other image, it could be an image of an owl or image of a lion, is our negative example. So the embedding model will learn and it will bring positive example closer to the anchor, and it will move the negative example farther to, to the anchor. So this is how it, the contrastive representational learning works. So if you could see, so we encode all these three images, and then the idea here is to minimize the distance between anchor and positive image and maximize the distance between anchor and the negative image. Now, when we have multimodal data, that's what we do. Now, irrespective of the modality, if they mean the same, so if we, let's say we have the anchor as a video where a lion is running, and then positive example could be an image of a lion sitting on a rock, or a text which says lion is the king of the jungle, and then there could be a completely different sentence and a completely unrelated image. So these could act as a negative example. So when we create multimodal embeddings, irrespective of the modality, the positive and anchor would come closer, and negative and anchor will have distance, more distance between them. So how do we apply contrastive learning for multimodal data? Like, how do we find contrastive examples? So one way is, we, let's say we have a text and then we have a corresponding image. So the text and the corresponding image, so text could become the anchor and the corresponding image could become the positive example, and rest all other images or rest all other text actually become negative example. So that's how we can find contrastive examples. So you can see, for text and for image, it become, for the text, the corresponding image becomes the positive example and rest all others become negative examples. So multimodal embeddings gave birth to large multimodal models. Before we understand how LMMs work, let's recap how do LLMs work. So we know that majority of current large language models are pre-trained models, and they are auto-regressive. Basically, they generate text one token at a time. Future tokens are conditioned only on previously provided or generated tokens, and unsupervised training was done using next token prediction on trillions of tokens. So that's how LLMs work. How can we apply the same concept on multimodality? As in, how can we apply the same concept on images? So if you see how LLMs work, if the example is Jack and Jill went up the, and based on the probability, it basically predicts the next word. So if there are many other words like apple, llama, large, mountain, big, peanut, hill, watch, if you see, the maximum probability is of hill. So model will predict the word hill. So that's how LLMs work. Now, if you recall, in computer vision, we assign every pixel of the image a number. So we convert an image into a 2 or 3 dimensional matrix. But in vision transformers, instead of converting each pixel into a number, we actually divide the image into multiple segments, and then we train the model to predict the next patch of the image. So if you see, if we have an image of a cat, the image is cut up into patches, and using patches instead of pixels, we make it computationally efficient to process images, and each patch is then embedded and passed into a transformer, right? So if you see here, we passed the patches, and then based on that, it will predict the word or what it is. So that's how vision transformers work. We also do visual instruction tuning. So in that, basically we have this input as image and text. So image is a painting, and the text is who drew this painting, and the output is Vincent van Gogh. So that's how we basically fine tune the model. So with different modalities, the input is of different modality, output can be of different modality, but that's how we fine tune the model. So if you see, we pass the images and the language, which is, or the text who drew this painting. Both the things were passed to vision transformer as well as the large multimodal models, and in the end we get the answer. So that's how basically we visually fine tune, or basically this is known as visual instruction tuning. Now, what are different applications of LLMs? We are already using basic applications of large multimodalities where we are processing images and text together. So, for example, we can give this image to the model and we can ask what is the color of the book, and LLM can generate the answer green. Similarly, we can also say describe this picture for me, and I think this is very common. People are actually asking models to describe the pictures and asking questions, what is present in the picture, and then you can see LLM has generated the result that a big red dog and a little girl reading a book. So we all know the basic applications of LLMs. One industry application is multimodal RAG, and I think by name itself, you must have understood what exactly we are doing here. So in normal RAG, we retrieve text. So we have text which we store in a vector database. We retrieve and then we generate the answers based on text. Now with multimodality, with multimodal embeddings, we can actually store images, text, video, and voice as well. And then we can actually do multimodal RAG. So now we have a vector database where we are storing data in any modality. When prompt comes, we'll retrieve any modality which is relevant, and then we pass it to the LMM, and then basically it will generate the response based on that. So multimodality RAG gives us the opportunity or the freedom to store any kind of data. We are not just restricted to text data. And why we could do this? Because we have multimodal embeddings now. Another use case where we can use multimodality is that now we can have text to any search. So now it's not that we give text as an input and get text as an output. We can give text as an input and can get any the basically we can get output in any modality. At the same time, we are not only restricted to text as an input, we can give input in any modality, and we can retrieve the answer or generate the answer in any modality. So basically, with multimodality, we can have any to any search. Now, what are the different industry applications? One very important use case is that if we have hard copies of receipt, we can actually extract information from those images, and we can actually generate electronic invoices, right? So that's one. Second, if we have anything where the data is in image format, we can extract that. So here we have the table which is in image. We can actually convert that picture into an Excel sheet. Similarly, we can also ask LLMs to describe the image, as in we can also ask LLM to describe the flow chart. So it will explain us that how what exactly it can see. So you can see that it's a flow chart. It can explain us. It can also explain the images. So here it's a graph, and we can ask the LLM to explain what exactly it's doing. We can say that explain what you see in this image, and model can say that this image shows the historical chart of the S&P 500 index. The S&P 500 is a stock market index that tracks the 500 largest publicly traded companies in the United States, and the index is considered to be a leading indicator. So basically it's reading, so whatever it's saying, it's S&P 500 index, it can tell us about the index, it can see what exactly how the index is performing, all those kind of things. We can also have like uh, tables written in image, and we can also say that I have a SQLite database set up in Python using SQL Alchemy, help me implement tables for the following schema. So basically reading that image, it can help us in designing a database schema as well. So we know that with large multimodal models, we can have multiple use case for industry purposes as well. So this is what multimodality is. The idea here is to create multimodal embeddings, and once we create multimodal embeddings, we have access to multiple use cases. So this is what multimodality is. Thanks.